So far, that's been the thing that's not worked.
Hit record.
My intro to engineering class on Tuesday, I hit record, everything's fine, only a minute and a half recorded. Yeah, so we got those kind of fun. So I will get it uploaded as quickly as I can, that we can make it in there. I have not looked to see if this one actually worked, because this one was off my laptop, so, you know, we'll see. So what we've got in here, and so what I intend to do for those parts that we're going back into Physics 1 and bringing it back, I'm putting in my video. So this part of Hooke's Law, if you look it up in your book, you're going to find it back in the force chapter. Okay, you're going to find it back there. Remember, force, okay? What are the units of force?
Newtons.
Thank you. Or, if I'm doing engineering, what's my other unit for force?
Hertz. No, that's frequency. Is it kilograms, joules?
No.
It's kilogram meters per second.
Kilogram meters per second is a Newton, or kilograms meters per second squared is a Newton.
Pound force.
Pounds are force. Slugs are mass, pounds are force. So in Hooke's law, F is equal to mass times acceleration. If I'm dealing with a weight, the only thing I don't like about the first pivot interactive is it doesn't tell you what each of the weights were. I didn't see it anywhere. But those of you who have used the Hooke weights before are pretty sure they're what?
50
I thought it said
kilograms.
50 right above the video.
It may have, I just never saw it.
It said each of the weights is.
Okay, I just never saw it on my version of the video. I just never saw it. So I did use 50 grams because that's what it actually looks like. Remember, if it's in grams and I multiply grams times 9.8 meters per second squared, that is not a Newton. I have to make sure I do my conversion. Okay? And you guys can flip the ruler upside down. So you don't necessarily have to do, you know, you can do it whichever way you want to do it. But I have done the clip of reviewing Hooke's law from Physics 1. It's in here so that you guys can actually review it. And how to determine the spring constant. So I actually calculate the spring constant doing it this way. Okay? They've also got pendulums of variations of length. I've got my other lectures that are there. And I would like you, and I think you guys all saw, that I want you guys to do the video notes file. I want you to do it for the introduction to simple harmonic motion. That's the one I want you to do it in, and I think where I have you turn it in, it actually specifically says, do the introduction to simple harmonic motion.
When does that due?
Friday, I think. Is that what I have it on?
Yeah.
You want us to take pictures of it, upload it?
Yeah, take pictures and upload it. Partially because that way I don't lose it, okay? Me going back and forth between two different campuses and everything else that's going on, it's much better that you take a picture of it and upload everything. And if it doesn't want to upload, go ahead and email it. You're not on a Mac, or are you on a Mac?
No, I'm on Windows.
Okay. Anybody who's on a Mac, please do it in Google Docs or something, because I cannot get Blackboard to look at the Mac files. It is a pain in the tush. You also know, just in case, that your notes feature on your phone can work as a scanner, as well as the camera. And it is my intent, I didn't do it today because if anybody had walked into my office this morning, they saw that I had all three screens. I had 2 Zoom meetings going on at once. All 3 screens up because we were doing the American Chemical Society Council meeting for the meeting. And one of my jobs was helping to record and track votes. So I had several different things up, and it was like they were still going on when I left. So I did not disconnect my computer to bring it. I will you know, I have no problem with, even if you're physically in class, having you zoom in with your phone on the Zoom link or zoom in on the computer. We just got to turn the sounds off and mute and not connect audio so we don't get the background feed squelching yucky. Because I really got to using the chat feature during the summer. Being able to chat back and forth on there, because you guys know I talk fast. I mean, with you guys, you all know it. So it's like, slow down, hang in there. But if you put it in the chat feature, even if I don't get to it, it's something that I will take and add back into the class. So I did get to really using it in Dynamics. We used it a lot, and it worked out really, really great. The other thing is in the chat feature, I can actually upload a file for everybody so that you have it on your computer, and you guys can save the chat, and it will save all of that stuff in there. So I really do like the chat feature. I also like the poll feature. So that will allow us to use the poll feature, and especially since we've got people hither, thither, and yon, we've got another one. Jesus, are you on? I think we were going to have one more join us. Jesus Garcia is possible to join us in class. So that's what I want to do. So I'm going to actually use our lecture time to do a few more interesting things rather than do kind of the bulk of that part of the lecture. But that means what I end up doing then, guys, is I give you all kinds of cool stuff. So I'm going to show you we're going to go ahead. This is the PowerPoint I'm going to use for today. And we're going to start, and we'll do a slideshow. Okay, so our author, which is one of the reasons like I really like cats, I really like her. She's given us a couple of things. She gives us the idea of simple harmonic motion. There's a lot of things that act as you'll hear a lot of different terms. You'll hear a simple harmonic oscillator. You'll hear simple harmonic motion. You'll hear the wave functions of everything. You're going to hear this a lot. There are a lot of physical systems that we can describe using simple harmonic motion or a simple harmonic oscillator. In chemistry, if I have a covalent bond, that's the one where they're sharing the electrons back and forth, right? If I have a covalent bond, and I can set up a vibration in that covalent bond, that vibration can act as an oscillator. We use that in crystals because if you go back and you look at old time watches, they talk about a quartz crystal watch. We're dealing with a vibration in the quartz crystal watch, a natural harmonic in that watch in order to give us our time and use our timestamp. So we describe an awful lot of things using a simple harmonic oscillator or simple harmonic motion. Physicists also use the term oscillation and vibration interchangeably, but they aren't, okay? They aren't really the same thing, okay? An oscillation is going to give you a periodic motion, like the bouncing of the object on a spring, or the rotation around a unit circle. So when we actually did angular frequency and angular motion, we talked about what was going on around the circle, and we have those pieces. Vibration is a little different, okay? But the reason we do this, and the reason I start with simple harmonic motion, is we're going to do simple harmonic motion and we get into sound and waves, because that's what's going to happen when we get into electricity, magnetism, and optics. They're all waves of some sort or type. These are mechanical waves. Sound is a mechanical wave. And we get into sound in chapter 17. But sound is a mechanical wave and it's related to a vibration. If I do not have a medium, such as air, wood, water, or something like that, I'm not going to be able to generate sound. Sound has to have a medium there, and it's going to be what they call a compression and a rarefication. So if I'm looking at a tuning fork, what the tuning fork is doing is creating a buildup of the air right next to the fork, and then it's going to allow it to relax, and it's going to compress the air, and it's going to relax, and it's going to compress the air, and it's going to relax, and it's going to compress the air, and it's going to relax.
It has a compression and a what?
It's called rarefication. Compression and rarefication. Yeah, next week, or maybe even Friday, you can't talk about sound without bringing a Slinky. Slinky is the best demonstration device of all time when it comes to start talking about waves. Okay, because we have different types of waves. Totally different types of waves. So we get it. Now, one of the things I want you to look at on the GIF that I've got up here with the up and down motion and the circular motion there, if you imagine a pin on that little green object, and you take a roll of paper towels, or a roll of white paper, okay, and you let the pin, and I'm pulling that paper away, so the paper as a function of time, I'm pulling that away, what kind of a curve is going to be drawn by the pin on the little green dot? It's going to look like a sine wave. Or it's going to look like what?
A cosine.
It'll look like a cosine wave. What's the difference between a sine and a cosine wave?
Where they start on the origin.
Well, where they start on the origin, but we're going to call it something different. We're going to say phase.
Phase.
Okay? The difference between cosine and sine is 90 degrees. And we're going to call that a phase angle. Okay? We're going to call that a phase angle. So we've got that oscillation, we've got that vibration, we're going to call that a phase angle. A couple things I want to remind everybody. Period stands for the time to complete one cycle, start to finish. So if I'm back on that little green dot around the circle, the period is the time that it takes to get all the way around the circle, one time. If I'm doing it on the oscillation of my little object, if I start at the top, go all the way down to the bottom, and come back to the top, it's going to be that all the way back to the top. So the period is for one complete cycle. We actually end up using frequency more often. And frequency is the number of cycles per unit time. So let's say I have a tire. Let's use a bicycle tire. And we've got the port where I'm going to fill up my bicycle tire, right? I can calculate the frequency based on how many times that thing goes around over a unit time. That seems to be one of those consternations that people have is, it says, well, they didn't give me the frequency. Well, it told you it did 10 revolutions in 10 minutes. Well, if it did 10 complete revolutions in 10 minutes, yeah, it did give you a frequency. You put the 10 divided by the 10, and it's 1 revolution per minute. Or 1 over 60, right? If I'm doing it in seconds. 1 over seconds is a hertz, so we have our units. And just to remind people, we have an angular frequency, and the angular frequency brings in our 2 pi over the frequency and our 2 pi over the period, or 2 pi over.
Are you using the doc cam, Mrs. Woodblack?
No, I'm using the screen. You should be seeing a PowerPoint.
Okay. I was just making sure.
Okay, no, I don't have the dot cam. I don't have the dot cam. So we're using those things there. Now, those of you who had me last semester knew I beat on you about units and beat on you about units and beat on you about units, right? Unit analysis is going to save your hiney. Well, I hate to tell you, in Physics 2, unit analysis gets cumbersome. When we get to electricity, we're going to define things like amperes. We're going to define things like Henry's, we're going to define things like Faraday's, and the unit analysis does get a little funky. You can go back and actually do it and generate it all, but it will get a little funky. The other thing that you got to remember when you're working with these things, that my angular frequency is typically in radians, not degrees. So when you're on your calculators and you're looking at this kind of stuff, you've got to make sure you're accommodating your angular frequencies. So when you're plugging in the numbers, first thing, if WebAssign gives you the it's not right, double check to make sure that you're actually putting in things correctly. Okay? You want to make sure that you're actually doing those things correctly. So we've got those key terms. So let's look at periodic motion. So this chapter in CATS, she actually does this as special cases. Okay? In the book, she's doing this as special cases. We're going to look at that simple pendulum. We're going to look at the bouncing up and down of the spring. Okay? And in the videos that I already have posted, we're kind of describing that, but I'm kind of giving you more of the overview and the physical part of it rather than sitting here boring you with the derivation of those different equations. But we can do a variety of different pendulums. We can do the simple pendulum, which is like on my weight. And the simple pendulum, how that's defined is that whatever my rod is, has got sufficiently less mass, and most of the mass that's being controlled is being controlled at the end, which is why we do a washer at the end of a string. Okay? When I have a physical pendulum, I have to worry about the distribution of the mass, because it is going to impact it. So if I have like a grandfather clock pendulum that has that big metal bar, I've got the center of mass of that big metal bar, and I have the center of mass at whatever weight is at the bottom. And that's going to be a physical pendulum. The other interesting thing about physical pendulums is I can make a compound pendulum. I can put a little pin in there at that one point, and I can get some really cool movements and really cool motion. And we do that in dynamics. That's just because it's fun. For us, in this class, I want you to focus on the simple pendulum, and I want you to focus on the spring block system. I'm just pointing out the physical pendulum part for you guys, and I'm pointing out the torsional pendulum for you guys. I am not so worried you're not going to necessarily see those things on the test or anything. But I want you to be aware that those are out there, because when we get to dynamics, which for most of you will be next summer, E6. When we get to dynamics, we actually bring that stuff in. So I just want you to be aware that, hey, you can go back and see it. But the torsional pendulum is doing the rotation like a disc around a central point. So think about, let's see, what's a good torsional pendulum type of a vibration? So a lot of you people have played with a frisbee at the end of a stick, and you twist it and you're getting a twist back and forth, or you're getting a rocking motion back and forth. That's going to be more of a torsional pendulum. You're doing a twist rather than in the plane. So torsional pendulums kind of get into 3 dimensions. We start playing with that 3 dimensions. But again, whether I'm using a cosine function or a sine function, I'm going to make the choice based off of a phase angle. When you guys do the physical lab, when we actually go in and we're going to do the bouncing of the weight on a spring, we're going to use sine, but our book is using cosine. No, it doesn't matter, because all you have to do is change the phase angle. And you can use either one of those to describe. So, let's look at, like I said, that first video is going to give you where these 3 equations come from. Our book uses cosine, the lab will use sine, And we get our three equations here. So let's think about what's physically happening. I've got my block on the end of a spring and it's bouncing up and down. We know if we're at the top and we know if we're at the bottom. That's something that's going to be called the amplitude. In this case, on the screen, we see it as Y max. And that's the deviation from the center. The center line, Y max, is going to be from wherever my 0 is to the maximum value of Y. Or it's going to be to the minimum value of Y.
So the amplitude?
That's the amplitude. So Y max is going to give me the amplitude. Because what's the maximum value of cosine?
Like normal flat cosine?
Yeah, cosine. What's the maximum value? What's the biggest number cosine can give me?
1.
What? What's the smallest number cosine can give me?
0.
Negative 1. Same for sine, right?
Yeah.
So if I multiply that times a constant, guess what happens? That constant is going to tell me the amplitude. So if I have a spring that's only bouncing 10 centimeters, or I have a spring that's bouncing 100 centimeters, I'm going to get, that's where my amplitude's coming from. Okay, that's where my amplitude's coming from. So when I'm looking at my sine wave or my cosine wave, well, if I want to find out that whatever my Y max is, I'm just going to read it right off the graph. The wave function gives us a heck of a lot of information about our system. So if I have this as being, 6 in front of it, and we say that's 6 inches, I know this thing is bouncing 6 inches. So it's going to tell me what it's bouncing at. It's going to be bouncing 6 inches from, quote, equilibrium, where it is in the middle. It's going to be bouncing up and down. So that's one of the critical things that you're looking at. Now, how fast it's going up and down, or its frequency, I can have it moving 6 inches up and down. I can have it do it slower. I can have it do it really, really fast, right? So that's where the angular frequency times the time is. It's going to give you that part of the motion. So the first one is giving you its position. Where is my little mass at any given time? As it's going through its motion. Where is it at any given time? Now, let's think about this. I've got my little object bouncing up and down, right? Got it bouncing up and down. What do we know about the energy at the very, very top?
That it's
It's all going to be what?
Potential.
It's all going to be potential energy. As it goes through the equilibrium point, what kind of energy is it going to be?
kinetic.
It's going to be kinetic. And if it goes to the bottom, it's all going to be
Potential.
potential because it's got a restoring force because it's on a spring, right? All right, so if I think about it that way, what's the velocity at the very, very top? 0. What's the velocity as it goes through?
Yeah, it's
Max.
It's going to be at its max. And what's the velocity at the very bottom?
0.
Because it's changing direction. That's my first derivative of the position. The negative sign comes from taking the derivative of the cosine, and I'm going to get that first derivative. Remember, taking my position, taking the first derivative with respect to time of position is going to give me velocity. So if I know my wave equation, I can calculate the velocity at any point on that system. I can get that calculation of the velocity at any point on that system. Now, we can also take it one step further, right? The second derivative, or the first derivative of velocity is going to give me acceleration. The second derivative of position is going to give me acceleration. So I can get my acceleration. So I can do two things. Getting these systems, if I gave you that y is equal to 6 cosine 2 pi t, you can tell me immediately that 6 is the amplitude, and you can tell me that the angular frequency is 2 pi. Because you can read it right off of the wave equation. Or if I give you a graph, you can plug it right in. So having those wave equations can describe the motion an awful lot. Now, where's the practical application of this? If you go into chemistry and we're looking at vibrations, If I do infrared spectrometry, I am looking at those signals that are coming from that. I can tell you what kind of bond it is. Is it a double bond? Is it a single bond? Is it a carbon-hydrogen bond? Is it a hydrogen-hydrogen bond? Is it an oxygen-hydrogen bond? And if I can tell you that, I can start giving you the chemical structure. So understanding and using simple harmonic oscillators and simple harmonic motion, we can describe a heck of a lot of things. We can describe how things go around, how the motion of a pea on a Pirelli tire is going around. We can describe the motion of a merry-go-round. We can describe pendulums. We can describe a heck of a lot of things. And it turns out Mother Nature likes simple harmonic oscillators. So getting this part really makes sense. Why do I start with this? Is because we're going to get into sound. Sound is a wave. We're going to get into light. Light is a wave. And this is the start of our wave functions. This one is only a function of time. When we get to the next chapter, we're going to talk about a pulse down a string. I can send a pulse down a string, and we can watch that wave travel down the string. So not only do I have it as a function of time, I have a function of linear position. And we're going to expand these wave equations to get you that linear position. So we're going to add to this. Other things that it can tell us about the system. If I go back and look at Hooke's law and we talk about a spring constant, I can start looking at mass. And we find out that our angular frequency is going to be related to the spring constant and the mass of my object. So if I have two hydrogens at the end of a bond, and I'm looking at the types of motion that I can have, it's going to tell me something about what angular frequencies I can get. So being able to really, really look at these things makes a heck of a lot of difference. So we can get that piece, and we can explain and look at our systems a lot. So, couple things that we get. One, we've already talked about the energy. You can look at these energy diagrams going back and forth. You can look at the energy as the energy in the system goes through there. And what we also see, and we can expand this to dampening. We can add friction into the system, and we can get dampening of the system. And that's what this one is going to show you. You're going to get that dampening system out there. Pendulum is a simple harmonic motion thing as well. We can dampen the pendulum. We can get the same types of curves with pendulums as we can with that bouncing of the spring. But the spring gives us up there that works out really, really well. Okay. So, I want to go back because I got some cool stuff. So let's kind of look at one of the things that I am doing, okay, is I'm really, really trying to give you the section of the calculus book where they're going to derive the same kinds of things that we're talking about and give you the math. Because what you're going to find this semester is we're going to make an observation. We get into static electricity. We're going to make an observation, and we're going to pull the math that goes with that observation. Faraday was a crap mathematician. Maxwell was a great mathematician, but a crap experimenter. But he was able to take what experiment somebody else did and give you the math. Gauss. We're going to talk about Gaussian surfaces. We're going to talk about Gaussian distributions. We're going to talk about a lot of that kind of stuff. Gauss actually brought in a lot of that math that he derived. A lot of what we see comes from trying to explain the physical phenomenon that we are talking about. So if you think about that simple harmonic motion as a sine wave, now we've got the mathematics actually describes some physical motion that we experience all the time. So what you're actually going to see is you're actually going to see the calculus derived. from the physical properties from which it came. We're going to try and sew that problem back up together. So you've got, I'm using the OpenStax book because of course it's totally free, right? And I'm actually putting you back into where the mathematics is. You guys have seen that I've used hyperphysics before, so hyperphysics is in here. It's got the bigger pictures and stuff, and you can actually look at this part, and it's got the equations, so you can play with it a little bit. And so you can actually kind of use it, so it's a great tool. Then Flippin' Physics has got some really good GIFs that we can look at how we do the spring mass system, where you've got your amplitude. Let me scroll that down just a little bit better. You've got its restoring force, and you can see it create the oscillation back and forth. So you can do, so we don't necessarily have to do it from up and down. We can do it from side to side. We're going to do it up and down in the lab. And the only difference about that is that we have an initial starting point that's a certain distance away from our detector. So we can throw a constant into our wave equation. It also gives you the bouncing up and down one, right? One we've been talking about, that bouncing up and down one. And it gives you the one that's going around the circle. And you can track how it's moving through the sine wave, or the cosine wave, as your case may be. Because remember, the only difference is 90 degrees, plus or minus pi over 2. And then I've got, and then of course it shows, it's going to give you the velocity and the acceleration so that you guys can actually look at it. So the GIFs are really going to help you kind of get a good visualization. And hopefully, this is going to give you, when you start working on the pivot interactives, where you're trying to, first calculate your spring constant, and then actually do your motion, you'll be able to get that going. And let me see, what else have I got in there? That's the Flippin' Physics one. Oh, this one has got some interesting, it's got some interesting demonstrations of some other harmonic oscillator ones so that you guys can go back and look at it from a practical point of view. Okay, I think I'm going to stop there because brains are probably full. And that way you guys can get a chance to look at stuff and get stuff going. Questions? You guys good over there in Enid? Colton, you okay?
Said it logged them off, but then you get back on.
Yeah.
How do you want us to come here on Friday in ITV, or how do you want us to do Friday's class?
That's up to you. We don't have a facilitator, so it's up to you. If you want to zoom in, that is fine with me. I don't have a problem with that.
Wait, so you're not here on Friday?
I'm in Enid. I teach from the Enid side on Fridays. It will broadcast over here. At least that's the plan. That's the plan.